Conversation with one cell phone. I jump on 85, on 75. I said, no, the Jerry told me no.
All right.
I've got a feeling, I wouldn't mind if I ever have to use this. It's gonna be an emergency, probably a long-term emergency. And there probably won't be any bureaucratic regulators around to be bothered with. You have to practice on using it, see? Yeah. And go around and use the radio and do my propagation, know how to orient your radios, all that kind of stuff. You have to tenderize your brain. When you lunch after class, I'm gonna be, I won't be able to teach anybody anything. You'd be surprised. Okay. You're supposed to be here.
Be able to see them.
See what, more?
Yeah, maybe turn off the front zip lights.
I think I need to get closer.
Hey, you can wheel up a chair, pull up a table, whatever you'd like.
I'm ready to go.
Just leaving this up here for us.
So how do we get onto the live stream, the streaming?
So I sent an email link this afternoon that has the PowerPoint. So it's got all of this stuff here. So it's got the PowerPoint for week 1 and then half of the one for week 2 because I just started filling that one out.
Okay.
And then it also has the YouTube channel. And so here's some short URLs for that. But I emailed those to everybody except, well, the Eds, because I don't have your guys' contact. But everybody else got it.
Don't let us put any pressure on you.
Oh, no. You know
How's
what,
it going?
I do have
I'm
an
here.
email, it's just that I don't usually word it. As I told you, I'm not into social media.
What? I'm ready.
I have not used my email in half a year.
It's a good idea.
Here's some material for you.
Just
No, thanks, I just finished dinner.
And then you said it-
Had a second piece of bread, some stuff.
Something's on your email.
it in the car. Yeah, I know how to work it. It's gonna be
Let's see.
Then we can, if something comes up the last minute, we send out an email.
I haven't checked.
You don't have to, send out an email, and then you look at it, and you say, oh, there's no meeting, there's no file. Hi, Tom. Hi, Mike. What do you know? I don't know much at all. Oh, that's what I know. I know the less I know. Oh, yeah. Just through association. Yeah. Well, we're supposed to have about 14 people, so I guess Bart. No, I emailed this.
You can lift the, on the bottom right side, there's little levers. You can increase the height if you want.
Yeah, just lift it up and it'll go right to the floor.
I'm looking for an easy chair, something with armrests.
There's, this one has armrests. Okay, I'm just like, switch them around. They work either way. See if anyone's wandering around here.
Did you get your daughter back
You might as well serve at the base.
airport and everything?
We did. We drove over last night, spent a night in Bucktown, got her to the airport. 5 minutes flat.
Oh, that was good.
It was.
Ask anybody who knows me.
Why would they put that there?
I have no idea. And the older I get, the worse I get.
Well, you can call it home, I guess. Or the phone.
Yeah.
Well, it's only 4 minutes.
All right, teach us about this. Just need to know how to turn it on and yell for help.
Yes.
Do you have to do 7 or something?
Who you
I did 9. I don't know, I don't know.
I
Forget
got
it, it's too
911.
late anyway.
You didn't say nine. That's not a good thing.
Well, I guess I can stand out there and see if you come.
Thank you, Roger.
I'll go see if it's good.
Pretty good lady. You missed you on Saturday.
Well, I was taking care of funeral stuff, so
I know, but we just, you know, we missed you.
did you, was it a successful hunt?
No. That thing is gone.
I looked at a couple pictures and I seen that Chuck was out there with you guys.
Yeah.
Didn't have any other divers.
Nope, Chuck and Lynn.
Looked like you had a
What do you
pretty
think
good
of
crowd
a
of people.
Yasu
But
F-18?
it was gone, it's gone.
It's,
It's in the silt.
well, it's down underneath that tall grass where it's at.
What do you think
Yeah,
of
on the
a
tall grass.
Yeah, it-
Yasu
That-
FT9918?
That deep down, that's
At least.
least, in some places, I heard it's at least that deep down.
And
A lot of stuff in the
I
garage.
don't know, I guess over the next year, I'm gonna try and get, see if I can't save the money to try and get my equipment kind of straightened out.
It's a nice certificate. It's complicated.
Yeah,
Do you get kickback from Lynn every time?
Well, that's the first step, getting the
2
certification.
hours, you know, still haven't figured it out.
stuff. Lynn was talking about,
Of
he
course,
might
I
know
know
somebody who
somebody
can come up and do the class.
maybe 12 years. I do know somebody that could come up. He'd prefer to go there.
Daryl has one
He
and I
would
just,
be willing if the class
So
was
impressed.
come up, but class at all. He's not coming up here.
yeah, I like it that it's 12 volts too.
Right, it'd have to be,
Well, all there you can.
yeah,
I didn't know that.
and I've got a couple, if.
Even though-
Mine's a 12 volt. I gotta
If
check.
you're not here,
All right, so then you're on price.
I know at least one 16-year-old.
Oh, I didn't
know.
Well,
Like them going to build. It's so small.
All right, shall we get started? And then if anybody else shows up, we'll let them catch up.
2/3.
Yeah, well, people are here on time, let's get going, and everyone else can play catch up. So, welcome to the first class I'm teaching. Sorry if it sucks. You guys are guinea pigs. Comment sheets will be thrown away. So, here's some information. I emailed this to everyone but the eds. This has a link to the folder where all these PowerPoints are located. So if you missed something, you can always go back. And a YouTube channel where this is currently being live streamed. So as an overview, Jim Stiff, I'm your instructor. I guess I'm just like a guy who is trying to teach some people because Tom keeps twisting my arm about it. I'm a science instructor here. That's why you're in my classroom. I've been a tech/general since February. And hey, Travis, here. And I've been an extra class licensee since May, so I have not been in this business very long. I'm also the Weston County ARES, the Amateur Radio Emergency Service, emergency coordinator. Been that for like 2 months. So yeah, pretty new to this. So the more I learn about amateur radio, the more I don't know about amateur radio. This course is kind of a survey of what you need to know for the tech license. That's why we're going off the no nonsense study guide, because it's pretty much the information that you need to get your tech license. You will need a lot of time, like actually operating a radio, to learn all the stuff that you really need to know. Here's our schedule. You're here Monday, October 8th. We've got the next one is the 18th, 29th, 5th, 12th, and 19th. This was emailed to you. The only change is that the 18th is the date that we set for next week, not the 17th. And then the last one, November 19th, the Monday before Thanksgiving. that is the testing session. So we're not going to cover content. We're just going to be doing the test. So the material is in front of you, the KB6NU No Nonsense Study Guide. Printed it off because it's free, available, and is, like I said, no nonsense. What was going to happen is before class, obviously not before this class because you just got the book, but I'd like you to read the chapters beforehand. So we're going to cover 2 chapters a night. Read the what's going to come up next class period. I want you to write down questions. So if you're going through stuff, you have a question, bring it to class. Between somebody, we've got some people who have been in amateur radio for a while, some people that may or may not know some stuff and could answer your question. Then during class, we're going to ask questions. We're going to cover the next 2 chapters. Jacob, welcome. Here's your course material. There you go.
All the material for the course?
Yep, that's the book that we're going. That's our study guide. Are you going to stay or just drop them off?
I got this one.
Okay.
I'm not gonna see it.
And then after class, read the chapters for the next class, write down questions, and I highly encourage flashcards on a website called hamstudy.org. That gets you comfortable with taking quizzes, so it'll give you like a 35-question quiz, similar to what you'll find the day of the test. And if you can go through those and you're scoring consistently in the 80s or 90%, start studying for the general. Why not? Because after you take the tech, we can just go right on and give you the general test as well. Might as well, you're sitting here. It costs no extra because you're already paying the $15 to be here for the first test. Why not? Question?
Will it be an alternate testing night that you can come to?
We can make arrangements if you know.
I'm gone that week.
Okay.
We can
we-
make arrangements if I'll have a Dwayne or Katie or somebody come down. If he's here and I'm here and we have Katie or Betty, we can get a test.
Yeah. So we just need 3 test examiners. Tom's 1, I'm 1, and then we just need a 3rd. So, but yeah, definitely the flashcards are really helpful between the classes. So it's 10 days until our next class. Going through those as well as reading the chapters. Heck, read the rest of the book if you really want to. It's really good information. So this week, we're going to talk about electrical principles, electronic components, and circuit design. So that's the first kind of chapters and introduction in your book. We're just going to skip it. It just says how to use this manual. So the first 2 real chapters are electrical principles. So turn to page 5 if you want to follow along in the book. Make some notes in the book. Then this kind of gives you the idea of what's going to happen. We're just going to cover 2 chapters until the end. So we have some key terms. So for those of you that maybe have some experience in electrical engineering, don't have any experience in electrical engineering, we're just going to go the baseline here. So current is the flow of electric charge. So if I turn on a circuit, electrons begin moving through this circuit, and that's what we have as current. And sorry, Jacob. And also this slideshow is available online. I emailed it to, I don't know if I emailed it to your mom, but definitely your grandparents have it. So they can get you a copy if you need. Voltage is the electromotive force. That's what the EMF stands for. And it's the pressure that causes electrons to move through that circuit. So essentially the voltage is the force to push those electrons. And it does that by a voltage difference. So the electrons move down the electron gradient. And then we have resistance, which is, just like it says, the ability to oppose that electric current. So we'll run into every component has its own resistance. Wire has its own resistance. Even though it's a conductor, there is resistance in every component, especially resistors because they're built to resist. Alternating current. When I plug into the wall, that's what I've got. It changes its current, or it changes its frequency. Actually, we'll talk a little bit more about that. And it changes its polarity. So the stuff that's coming out this wall comes out at 60 hertz, which is actually it changes its polarity 120 times a second, which I have a diagram when we get to the page about AC versus DC. Direct current is electrical current that flows in one direction only, so it doesn't flip-flop like AC does. Conductors. So it's a material that easily loses its grip on electrons. So it's something that when you apply that voltage to it, it will give up its electrons. And then an insulator is one that has a tight grip on its electrons, therefore it doesn't allow those electrons to flow and inhibits the current to go through it. Any questions on any of the key terms? So I just use the ARRL's glossary that they have on their website. It has.
Slow down. I haven't taken handwritten notes in like a year or two.
That's totally fine. Any other questions? Would you and Terry like a copy of the material?
Yeah,
Just
that'd be good.
curious. And these definitions are also found in the in this book. Just is in a little bit more common language as well.
Okay, okay.
Thank you.
And so our basic circuit, the circuit has a battery, it has a resistor or resistance, so that's in the form of a resistor, and it shows its flow of current. Yes, Jacob?
I wasn't done with the key terms.
Okay.
Like, I only had two.
Would you like me to print you off a copy?
Sure.
Okay, I'll print you off that page.
Copy of this because I'm probably not gonna get even half of it.
Okay, so just remind me at the end of class, I'll print you out the slideshow handouts. So the basic circuit here is we have some sort of battery. And so I actually found out that each one of these bars represents a cell in a battery. Did not know that. So this has two cells in its battery. The long bar represents the positive voltage, so the circuit would flow this way. We have every component has some sort of resistance to it, definitely represented by a resistor. And current is represented by I, which is really confusing and I don't know why. So voltage is represented by E, stands for like the electromotive force. We measure that in volts. Current is represented by an I, and we measure that in amperes. And resistance is represented by an R, and it's measured in ohms. And so it's got the Greek symbol omega to represent that. And so amps are also known as, or amperes are also known as amps for short. So we'll use those interchangeably. Unless for some reason there's a reason not to use one or the other. All right, so here's where I was talking about where AC current switches its polarity twice a cycle. So once it goes up, so then it has positive polarity, negative polarity, and then goes back to positive polarity. This movement up here and down, once it crosses this, goes up, crosses down here, has a trough, that is one wavelength. And so when we talk about, wavelength, we measure that in hertz. And we measure that, 1 hertz is 1 cycle per second. And so depending upon how many cycles happen per second, we can say like that's 60 hertz. So like the stuff that comes out of our wall cycles at 60 times per second. So really fast. Direct current is something that we use in our radio equipment. So with our batteries, those are DC current. We use AC current to charge it, but we need some sort of transformer to turn it into DC current. The mobile radios, somebody was talking about 12-volt mobile radios. Well, those plug into the DC ports on your car, and so that's direct current.
Radio waves are simply transmissions of electrons passing through the air, correct?
Not electrons.
Okay, then what are radio
So
waves?
it's we'll get into characteristics of radio waves. I'm not sure what week it is off the top of my head, but it talks about the radiation coming off the antenna and how that's transmitted through the air. But it's not radiation like gamma radiation. It's on the electromagnetic spectrum, though.
Electromagnetic radiation.
Yes, exactly. Questions over AC and DC current? Okay. I will also tell you that no matter which one you have, if you shock yourself, it really sucks both ways. So
Alternating current can kill, DC cannot,
DC could still kill you.
if it's high enough.
Yeah. So we should find a way of live casting of a presentation. Looking at what Mr. Beam is saying because he's live chatting with me on the stream. So conductors versus insulators. So a conductor is something that has a loose grip on its electrons and will allow them to move through will allow voltage and current to move through a system. Insulators do not. So good examples of conductors would be like seawater and silver, gold, copper. And so these things you find, gold and silver are really good for contacts. Copper is really good for wiring. So that's why we use those as conductors. Insulators, everything that we find like on the outside of these conductors. So this, inside of here, we have a nice copper cable, but we sheathe it in rubber so that we don't shock ourselves.
A lot of layers of rubber.
Yes. And so
Otherwise, there'd be sparks jumping off of the cables when they touched each other.
yes, and that would be quite unfortunate. Glass, rubber, wood, dry wood, those are all good insulators. Plastic, I don't know if I said that. And so a good insulator is a bad conductor, and a bad conductor is a good insulator. Questions on that? All right, so series circuits. So this is very similar to our first illustration of a basic circuit. And so a series circuit has one path for the current to flow. And so this current goes through all the components and then loops back to the source, your battery. So any voltage across those components is equal.
If the resistance is equal.
If the resistance is equal, yes. And so your resistance, your R1, R2, if they're equal, then voltage would be equal across it. If they're unequal, then you can actually get into some math and figure out what the voltage is at each point along the circuit, but we don't need to know that until like extra class. So that's why the no nonsense study guide removes those formulas from your face. So because you don't need to know that right now, this is enough to get you through the tech level. But we totally encourage you to continue on with this hobby. And there's a lot that even I didn't learn until like I started meeting up with Tom and Terry and Janet and with the Weston County Amateur Radio Club. I never built an antenna until I hung out with Tom. So with series circuits, just has one path. Parallel circuits, you have multiple paths for the current to flow. And here we have two paths that seem very similar because it's got a resistor and then goes back. This second path has a resistor and goes back to the source. If you have two different kinds of resistors here, one may be stronger than the other, has a higher resistance, then the current would be different through them. And so electricity goes usually to the path of least resistance. So, yes, that seemed anticlimactic. Any questions on the difference between parallel and series circuits? Okay. So a lot of this, if you have any, if you have understanding of electronic components, may seem very basic. It does pick up later in the course.
No. I had just gotten down series circuit.
Okay, but I'll get you a printout, make any notes you want in your study guide. Ohm's law. So this is really important. This is something that they'll hammer into you, or I guess we'll hammer into you. And this is something that you'll have maybe multiple questions on the test. Your test is only 35 questions. If you have 2 or 3 questions like this, this is a big chunk. So Ohm's law is a relationship between voltage, represented by E, current, represented by I, and R, resistance, represented by R. If you have 2 of those variables, you can calculate the third with this silly symbol there. So when I took my test, the first thing I did is I wrote down this and then the power circle, and it made my life easier. Once I found this out, life was great. So how to use this is just draw this on your paper and then cover up whatever you're looking for with your thumb. So first question, these are actually questions that are on the test bank. What is the resistance of a circuit in which 3 amps flows through a resistor connected to 90 volts? So what are we looking for? So we're looking for resistance. So we just cover up the R. And so in math, if we have an E with a line here over an R, that's divided. So yeah, we're looking for 3 amps and 90 volts. So we just put in our variables. So E would be our 90, and I would be 3. So it'd just be 90 divided by 3. So it's 30. So our resistance is 30. And what's our unit for resistance? So who said that? Ohms. So our resistance would be 30 ohms. And another one, what is the current of a circuit? So we're looking for current. So we're covering that. With an I hate that. Okay.
Touch screen so you need it.
So covering up the current of a circuit with an applied voltage. So we got 120 volts and a resistance of 80 ohms. So how do we figure that one out? So covering that up still.
120's on top, you said?
Yep. So 120 divided by 80 is 1.5. So our current would be 1.5. What's our unit for current? Okay, amps. So because we measure current in amperes. And then finally the voltage, so we'll cover that one up, of a 10 ohm resistor with a current of 2 amps. So we have current, and since it's beside it, we're going to multiply it by resistance. So our current of 2 amps times 10 ohms gets us how many volts? Say that again, Travis? Okay. So this thing makes Ohm's law very simple. There is, you can find the, in your book, you also have some formulas to do it, but I find this pi really easy. Any questions about that? Recommend drawing this in your book. Jacob, you had a question?
Can you explain that in dumb terms? Because I have absolutely no idea what nonsense you just spouted.
Okay. So this E up here is your voltage for your electromotive force. This I is your current. And here, resistance for R. So whatever you're looking for, cover that up. And then put in your, whatever's missing here. So you cover up the I, so you're looking for current, put in the voltage, put in the resistor or resistance, and divide it. If I'm looking for voltage, put in my current, put in my resistance, multiply them. Or if I'm looking for my resistance, I take my voltage, divide by my amps, find resistance. So that's why I say draw this, sit down. You can write on your test. You sit down, and then I have it sitting there on my table. I just remember it ear. Not EAR, but just ear. But the A can kind of represent amps. But ear, and then the other one's pi, which I'll just get to. And so I just cover it up with my thumb, and it's there. I can remember Ohm's law. So the next one is DC power. And that one is pi. And since it's a circle, that makes so much more sense. And so with DC power, the P stands for power, which we measure in watts. And so Power is the rate at which electrical energy is generated or consumed. So when we talk about solar panels or generators, we talk about energy that's being consumed or generated. When we talk about draw on a battery or draw on an electrical system, we call that the load. And we measure that in watts. So we look at an incandescent bulb. It's a 60 watt light. And so that draws 60 watts of power. And power equals the current times the voltage. And it makes this nice shape. It's the exact same shape as the previous one. With Ohm's law, the I stays in the same spot. The only thing is that the E moves down and P goes on top. And so it's pi. And so this same principle works with this. So if I'm looking for power, which we measure in watts, so it says how much power is being used in a circuit when the applied voltage, here's our voltage since that's our electromotive force for E, and the current is 13.8 volts DC, and the current is 10 amps. So we cover up the P because we're looking for power. And how do we find what our power is? Okay, so how'd you find 130, Ed?
I times E, or the voltage of 13.8 amps, or volts times 10 amps. 138.
All right.
Times the decimal point over by 1.
So we just moved the decimal point over, and so it's 138 watts of power being consumed. And this is actually really reasonable because a lot of base station radios operate at 13.8 volts, and a lot of times draw about 10 amps. So that's something that you're going to run into in a base station. So another one, how many amps, and what's our symbol here for amps? Okay, I. So we cover up the I, are flowing in a circuit when our applied voltage, so which one's our voltage? Okay, so we put 12 down here, and the load is 120 watts. So when we put 120 here, so what's 120 divided by 12? Okay, so 10. So then we have 10 amps flowing through that circuit, where we have 12 volts, and load is 120 watts. Any questions on DC power? So that was the first thing I did when I sat down for my tech license, is I drew these two circles with the lines through them, and I wrote pi in one and EIR in the other one. And that took care of like 8 questions. It made life so easy. I was also nervous as heck, so that just having that written there made me feel so good, because I wasn't going to think about power equals current times voltage. I had pi. So these metric prefixes and conversions, you just kind of have to memorize these. So we talk about our base unit. So if we're talking about meters, so we have 1 meter. If we have 1,000 meters, that's a kilometer. If we have 1,000,000 meters, it's a megameter. And then we have gigameters, which we really don't use those. But let's talk about volts. Or let's talk about hertz, because we talk about hertz a lot when we talk about the kilo, mega, giga. So with hertz, that's our basic unit of frequency. If we have 1,000 hertz, we have a kilohertz. If we have 1,000,000 hertz, we have megahertz. Then we get into like gigahertz, which is 1 billion hertz, which is a lot. Then we come down, and this is pretty much just moving the decimal point over 3. So we start here, we move the decimal point over 3. We have kilo, 3 more, mega, 3 more, giga. And then on the way down, we can move the decimal point over 3 times. We get milli, and then we keep going over, and we got micro, nano, and pico. And this is, I don't know, a really good way of memorizing this. No, I don't really know any mnemonic devices. What?
mnemonic. You said it. I believe someone once said it's called mnemonic devices.
Well, either way, I don't know a good way of remembering this. I believe there's a song maybe, but I don't know that. So some questions that you might run into on your test are how many milliamps are in 1.5 amps? And so we're going from our base unit, and we're going to milli. So we're going to have to multiply this number times 1,000. So how many amps are in, or how many milliamps are in 1.5 amps? Say that again, Travis.
1,500.
Okay, so here we have 1,500 milliamps in 1.5 amps. So for every amp, we have 1,000 milliamps. How many kilohertz? Ew, capitalize that Z. I don't mean to capitalize that Z. How many kilohertz is 3.525 megahertz? So we're going from megahertz here, and we're going down to kilohertz. So what do we need to do? Okay, so we move the decimal 3 places. What direction? Okay, so we move it to the right. So we go move it over 3 times. So we have 3,525 megahertz. Or kilohertz, excuse me. So this one might just be something to try to remember. The kilo is really easy because we use kilometers. If we want to talk about watts, kilowatts, megawatts, gigawatts, that might help that direction. Bless you. Milli is really useful. We talk about millimeters, so there's 1,000 millimeters in a meter. We really don't use micro, nano, and pico that much, except when we're talking about really, really small things. Any questions on that?
Can you hold right there so I can get the notes down?
Okay. Are you copying this chart? Because I was going to.
Just the little notes here and there.
Okay.
Essentials.
Let's see. Find a way. Oh, is it in the book? All right. So.
Page 12.
Okay. So that's on page 12. Cool.
That whole slide's on page 12.
Yeah, because I did copy some of these questions because they're directly out of the book and directly out of the test bank. So the test bank has, I think for general, it's like 4.
Abbreviation for micro.
It is a mu, which is a U with a little stick on the front. And so these are questions that you find. I think there's 418 on the tech. Is that about right?
435.
435? That might be the Electoral College. I don't know. So it's about 400. It might, well, the new question pool, I don't know then. So I know with the old one, it was just north of 400. Which is also why, like, going through this doesn't expose you to every single possible question, but it gives you, like, a really good general knowledge of what's going on. The flashcards are really helpful for finding, like, going through and being able to see if you've hit every single question or at least been exposed to every single question. So when you go through that hamstudy.org, you can actually sign in, make an account, and it will tell you when, like, okay, I'm really good with these kind of questions. So I know a lot about electrical principles, but I don't know very much about antennas and feed lines. And so it will give you more of those kind of questions and will show you which ones you're proficient at. So decibels. So decibels are
Sound wave.
so decibels is like sound. Sound decibels are measured in a logarithmic scale, but decibels relate to a ratio, and so we talk about increasing power in certain ratios. And there's a formula that you can use to figure that out. You don't need to know that. That is, these things you can just learn for rote memorization later. I don't know if it's at the general level or the extra level, but you can then have questions about calculating these ratios. But for right now, you just need to know 3, 6, and 10 decibels. And these are on page, I think, 14 or so. Probably just have this out so I can reference pages as we
It
go.
is page 14.
Okay, page 14. Thank you. And so page 14 kind of has what I have up on the board. As you increase power, if you increase or decrease. So 3 decibels correlates to a 2-to-1 ratio. So if I double my power or I halve my power, that would be a 3 decibel change. You can have a positive 3 decibel and a negative 3 decibel. So if I go from 5 watts to 10 watts, I just doubled it, right? So it's a 2-to-1 ratio. That'd be a 3 dB gain. Or if I went from 10 watts to 5 watts, I cut my power by 3 decibels. And with 6 dB, that's a 4-to-1. So it's like going from 3 watts to 12 watts. I went for a 4-to-1 ratio. And then 10 dB, oh, that's not right. That should be a 10-to-1. Okay, so don't look at that up there for the 10 dB. Look in your book. It should be for a 10-to-1 ratio. I don't know why it says 2-to-1. And so that would be going from like 10 watts to 100 watts. So 10 watts would be like a QRP, like a really low power radio setup, to 100 watts, which is usually your full power base station without an amplifier. And it can get really big.
We have an amplifier
Increases.
in my house
For radios?
for ham radio.
Cool.
My mom already has her license and everything.
So we're going into chapter 2. If you guys want to take a quick break, stretch, use the bathrooms,
Water.
get some water, that'd be fine. We're going to go into different electrical components. We're going to talk about each one. We'll go from there. We actually, I don't know if you even need to know how to measure each one. Trying to think on the technical level.
How do you measure?
Well, like,
They get you by color as a number.
oh, you're talking about, yeah, we can talk about
I
that.
used to know that, not anymore.
I knew it in high school, 9th grade.
I
But I had
know.
a-
It's ingrained in the back of my mind.
Yeah.
I had a cheat sheet.
Well, I hated like the difference between like dark brown and black or dark brown and purple. Like-
Yeah, being able to take and actually,
Yeah.
Brown is 1, red is 2.
I remember gold is like a tolerance of 10% or is it
Gold is
5%?
5%.
5%. See, I always just like look up like, okay, what's red? Then it goes to number 2, then 3.
I can't even remember, when I was in high school, they gave us a mnemonic memory device for it. I used to know it and I can't remember it now. And it wasn't appropriate. I won't say it was.
Of course not.
A lot of this, I remember from that. Going, yeah, I remember this. Should just keep going at that point.
Oh, I need to get you your piece back.
Should get a stretch for a moment.
Are you a teacher?
Yeah, I teach in this room next door.
Or were you here last time? With the antenna you had? Or was another teacher?
That was that.
Yeah. Oh.
Oh, I could shoot that.
Yeah.
He has a brain.
One time. Well, we'll get it. I don't think he has a boy.
Yeah.
I don't know, we're gonna find out as we go anywhere. As long as it's under a foot, I don't care.
She mentioned
Yes.
activity this week.
You've been down, no
Take care of your daughter and you'll.
No, I don't care.
5 o'clock.
Yeah,
that's not right.
Move over through the calendar. Because, mom, dad, son. I would consider listing on there for her for all the days I've got activities. She's finally only got done seeing her pretty much every day, it's taken up too much. Now I understand.
Yeah.
That's not,
My brain's fried, so
So,
I'm gonna be here today, but that's fine.
I'll end up missing next
Too
week.
many game numbers for me. Oh, we got it really excellent.
It ain't hard to get through the, at least it's hard to get through security there.
No, it's not that bad. Line all the way out to Congress area out there today, and accuracy had already gone wide. Yeah, like 3, within 20 minutes, there were 3 different quotes. All at the same time. Quarter, 605.
And whoever did it, we forget. And it took us almost an hour to get through the airport security.
And then,
And then we had
yeah, the funny thing today, it was almost a half hour late debrief, because they had to light the road up on the line. So that first 90. But, over an hour longer to try and balance the map. Around,
No email?
luckily, we had an hour, 2 hour layover in Dallas.
All right, do we have everyone back? Yeah.
thank you, Mr. Stitt.
You're welcome, Jacob. All right, so electrical components. We're going to talk about the component itself. I'll show you a picture. I'll also show you a picture of the schematic symbol for this item. So we'll talk about resistors, because they're one of the first things that come up. They're these very nice and also usually very tiny resistance components. So they all have a specific value for their resistance. You know, some of them are 1,000 ohms, some of them are higher, some of them are lower. The way you figure that out is by reading these bars. So they coordinate to a certain value plus a, I just realized not all of them are oriented the same way, plus a label for their tolerance. So it could be like, okay, it's 1,000 ohms, but then it's plus or minus 5% or plus or minus 10%. And so most of them have a fixed value, except for what we call a potentiometer or variable resistor. So here is a basic resistor. It doesn't change its value. It just has one value, like 1,000 ohms. This symbol right here, where it's looped back on itself and has an arrow, means it's a variable resistor. So as you turn a dial, like if you turn a power switch on, you can actually change it to change like the volume of a speaker. That would be the use of a potentiometer or variable resistor. So as you turn it on up, it actually decreases its resistance so the speaker can get louder. You turn it down, it increases its resistance so the speaker gets quieter. And so these resistors oppose the flow of current, but to very particular degrees, and it's used to control how much current flows through a circuit. Any questions on resistors?
You could use electrical breaks too, so to determine around if the resistance doesn't allow flow of electricity going a certain way, you can stop the power from going from one unit to the next by putting a certain amount of resistors in.
So yeah, if you increase the resistance, to the point where the current can't, like it's so high the current can't flow, that could work as well. The next component that we want to talk about are capacitors. Capacitors, they store their charge in an electric field. And so a capacitor has two parts. They've got the anode and the cathode. And the cathode is the positive side, the anode is the negative side. The only way I remember that is the T of cathode. So there's a T there, and anode doesn't have a T, so that's why it's the negative side. So cathode always has the positive side. There's probably some weird component that says I'm wrong and has a cathode on the wrong side. And so what this does is it stores current until it reaches the DC voltage. And so they measure their, I guess I meant ahead of myself. So the ability to store energy in an electric field is called capacitance. So capacitors operate on capacitance, and we measure capacitance in farads. Farads? I think it's farads, because the thing is designed by Faraday. Or at least named after him, maybe? I think so.
As in the Faraday cage?
Yeah.
The cage that shields objects from electromagnetic waves.
Yeah. I think that's named Faraday. Their schematic is this line. So you have the pickaxe and the T is on the positive side. The pickaxe is on the cathode side. You really don't need to know that. You should just be able to pick out a capacitor out of a schematic diagram. So you'll have pictures where it shows you schematic diagrams, and it'll say, what is component 2? And so they'll have 1, 2, 3 through 10 on the schematic. And so it'll just ask you, pick out this component, tell us what it is. And these things, just as a fun side note, they do not discharge when you turn off the power. They stay charged until they self-discharge later. So if you're working on an electrical device and it has capacitors, sometimes you shock yourself. I've done that a lot. My dad also used to charge them and toss them to his friends, and you grip them and you can't let go of them until it's done shocking you.
So basically, capacitors are unstable versions of batteries.
Kind of. So they're batteries that instead of chemically storing their charge, stores it in electrical fields for shorter durations.
Right.
And so our next term is a inductor. And so you're starting to find inductors in more and more devices, especially consumer electronics. So like watches, cell phones are now starting to get this wireless charging base stations. And those are all based on inductance. There's also inductance cook stoves. So you can like put one kind of pan on there, but another kind of pan, or your hand doesn't heat up when it touches it. They're kind of cool. But what inductance is or inductors are a small coil of wire that generates a magnetic field. This right here, this bar, you don't actually have to have a bar there. You have open coil inductors, and then you have ones that are wrapped around stuff like toroids. And it's the ability, or so it stores its energy in a magnetic field, and so the magnetic or ability to store energy in a magnetic field is called inductance. And that's measured by something called the Henry, which I believe is named after a guy that discovered it or worked on it. And really, the main thing that you need to know about inductors, other than that they store their energy in a magnetic field, and they store it in a unit called the Henry, is being able to pick it out of a lineup when we look at a schematic. So something that looks like a cold front, that's an inductor. Okay. And so here's another one, and this is something that I learned just the other night, is that this symbol, since there's only one big line and one small line, that's a single cell battery, like a AAA. Here we have two cells. So in a lot of your handheld radios, they operate on like 7.4 volts. Hey, Colby. They operate on 7.4 volts DC. That's actually two 3.7 volt lithium ion cells put together. That just blows my mind that you can tell from the schematic how many cells are in a given battery. So radios use a lot of kind of batteries. So there's lithium ion, which is rechargeable. Lithium, I don't know if any of them use lithium polymer, LiPo batteries, but you have nickel metal hydride, which they're starting to phase out. Non-rechargeable batteries like AA's, some radios you can actually get a battery pack that runs on AA's for a shorter amount of time, but you can use it in emergency situations. And carbon zinc batteries, which they haven't really made since the 70s and 80s, but there's a question still on the answer or in the question bank about which of these is not rechargeable, and carbon zinc batteries or zinc carbon batteries are still on there. So they're like really old AA's, and then the alkaline AA's became the heavy duty ones, and then people started using rechargeable ones. So you really won't use these two. You probably can't even buy the carbon zinc kind of batteries, but you really won't use AA's that often in an amateur radio, and maybe not so much the nickel metal hydrides, even though Mr. Beam just bought one that because the FT60 has nickel metal hydrides. Most of them will be lithium ion batteries for handheld radios. Larger radios can be powered by sealed lead acid batteries. So lead acid, like a 12 volt battery that you'd find in a car. You can also find like deep cycle batteries, and those are rechargeable. So when you turn on your truck or something, the alternator charges that up. And then you also have newer batteries that are like lead iron phosphates, gel cell AGM, which are glass. I think those are also sealed lead acid, but it uses a glass cell there. One of the safety notes that's on the test is if you short out the battery, if I just take the positive and negative contacts and spark them together, you can destroy your battery, damage your battery. It can also release toxic gases. Generally don't do that. Also, you can shock yourself. That's one of the things that's a danger of shorting out a 12 volt battery.
12 volt battery?
Like a car battery.
Oh,
Yeah.
that's a 12 volt battery?
Yep.
A car battery?
Yep.
Those things are huge for the amount of voltage that they carry.
Yep. And so the cool thing, or the interesting thing is that there's a difference between a deep cycle battery, which is designed to deliver almost all of its voltage before being recharged, and a 12 volt battery that you find in your car, which is designed to deliver a lot of what they call cold cranking amps, CCAs.
Small level charges.
Well, it wants to deliver all that energy really fast so you can start your car and then let the alternator recharge it, so then all of your stereos and heaters can run off of it. Any questions about batteries? Next component are diodes. So there's two types of diodes that you need to be aware of. Are standard diodes, which look like this. They've got a line, and then they usually have some really, really tiny numbers, right, Colby?
Okay.
Really tiny numbers. And so this line actually denotes the direction that it allows current, because diodes only allow unidirectional flow of current. Unless you put a lot of current the wrong direction, then it smokes. So on a schematic, this line here matches up with this line, and on the schematic, the arrow points the way that it allows current to flow. So if I put this diode in, it would allow current to flow in one direction, not the other way. Diodes are really useful for that. The second kind of diode looks just the same on a schematic, but has these like Harry Potter zigzag lightning bolts. Those are light emitting diodes. You find them in flashlights. You find them in, what don't you find LED? You find LED TVs. You find, there's my water. You find LEDs in lots of different setups. This is a really common one. So the positive end is the longer one there. They're useful for a lot of different things. Lights on your keychains, because they put out a lot of light in a very small package.
So in a circuit, would a light emitting diode be used to like tell you if electricity is still flowing through the circuit?
Yes, so an LED is often used as an indicator. So you can use LEDs for like lighting the back of your screen so you can see it at night, but also to tell you like, is there power on? Like if I flick on a switch, usually that like a rocker switch, there's usually an LED behind there to say, hey, your power's on, flick it down, power's off. Flick it on, light comes on, power's on. Good question. All right. Transistors. So this gets into a little bit more complicated stuff. So a transistor has 3 layers of material, which is like the biggest thing that they want you to know about transistors. You don't need to know that one's a source, one's a gain, one's a collector, base, emitter. Sorry, thinking about the wrong kind of transistor. So transistors can be used as switches. So before we had like microprocessors, we just had giant boards of transistors being used as gates. Transistors can also be used to amplify a signal, depending upon a given transistor's gain. And it's made of 3 layers of material. We don't actually need to know what the 3 layers are. I just use this diagram to show here's one layer, here's another layer, here's a 3rd layer. So a transistor is easy to pick out because it has 3 pins. I don't think anything else that we cover has 3 pins. So when you look at a diagram, you don't need to know one's a base, one's a collector, one's an emitter, and you don't even need to know what this arrow means. But being able to pull this out and say this is a transistor is important. And then one other kind, you only need to know that FET stands for field effect transistor. And that's really all the tech level needs for transistors. Transistors are also really fun if you want to build a kit radio, working with transistors, soldering, all that good stuff. A lot of fun. You can buy, what was our Pixie kit, like $10?
Yeah, they're $10 a piece.
Yeah, so you can buy, it's like a Pixie or Pixie 2. It's a little Morse code CW transmitter. Picked it up for like $10. It gives you the opportunity to do a lot of soldering, and also gives you the opportunity to burn it out.
Twice.
Twice. But it was a good learning experience. Any questions about transistors? They kind of replaced vacuum tubes, and so they're smaller, more durable, solid state versions of vacuum tubes. So schematics. And so this is something that will show up on the test, and it will just give you this and tells you what is this component? What do each of these things look like? This one, Tom, I was going to ask you, I think these are contacts, like female contact. Okay, that was the only one I wasn't sure about. But the rest of them, schematics. So the rest of them, let's talk about component 1. We've run into this before. The zigzag across the line. Resistor. Component 2. Okay, we got transistor, and that one is again the one that has 3 points of contact. So it can act as a switch, it can act as an amplifier. 3 we haven't talked about. What do you guess that is?
LED.
So not quite LED because it doesn't have the weird like triangle, but it's a lamp. I don't think that's actually on the test, but the circuit has a lamp on it, so I just decided to label it anyway.
Oh, that's right. Sorry. Yeah.
Yeah, sorry, that was kind of a trick question on my part. But they'll have lamps, so this would be more like an incandescent lamp, also used as an indicator. Those are mostly being phased out in favor of LEDs. 4.
Battery.
Okay, so we have a battery, and what direction is the charge going in this battery?
Positives at the top.
Okay, positives at the top because we have the long bar there going to the top. And so how many cells are in this battery? 2. And that's not on the test, but I just like asking that because I just learned it and that's exciting. So again, something that I didn't know, now I know. And component 5, we haven't covered that, but what do you think that is? It's the pitchfork thing.
Isn't that like ground or something?
Yeah.
Yeah, so here, the circuit's grounded at multiple points. This right here is a ground. So it's like we took a pitchfork, stuck it in the ground. And so that's a good way of, well, I mean, I don't recommend using a pitchfork, but that's a good way of remembering that's a ground. Or it's a rake. I rake the ground with it. So we'll run into other schematics like this. Sorry if this is a little hard to see. Okay, so this right here, I again looked at it and I wasn't quite sure. I think that's some sort of like voltage source. I wasn't quite sure. I saw one that had like a wave through it, which was AC. So I assume this is DC. Not 100% sure on that. Number 2, Tom, do you know what number 2 is? I wasn't quite sure about this weird white box with.
That's a fuse.
Oh, that's a fuse. Cool. Another thing I just learned. So 3. What does 3 look like? Okay, so Carrie, Travis, switch. So this switch is, so in the test, they're going to ask you, it's a single pole, single throw switch. So it's not a double pole, double throw like what you'd find on like a, oh, I don't know what I would use that on. But so this is just like the old mad scientist. I've got one for you. It's a lot. So this is my mad scientist coffee maker where a relay burns out. And so now I've got a single pole, single throw switch to turn it on and make coffee.
Cool.
So as this is the switch that's talking about, really it doesn't need the second pole on there. But if I got rid of that, it's a single pole, single throw. I just have a negative and a positive lead connecting that. And then I open the circuit's done, close it, coffee's being made.
That is cool. You brought that out in science class when you had medium class. That would have made class a lot more interesting.
I don't know, I just made that on a whim because we got a free coffee maker and it didn't work, so I'm like, let's make it work.
How long ago?
Component 4. So component 4, what's this on each side? So we have inductors because they look like cold fronts, and that's actually a transformer. So like this, which I pulled out of a microwave, we've got 2 coils of wire, and one's a primary winding, one's a secondary winding. You don't need to know that, but it's transferring. So as this one is generating its magnetic field, it's affecting the other one, causing it to generate a magnetic field. So these inductors are coupling across this transformer. And then the transformer is used to increase or decrease the voltage of the AC current. So this has really thick wires. This one has really thin wires. So they couple differently as they go through to get enough energy to make microwaves to then cook your food. This is also really heavy. I also have a tiny one, I guess, which is also really heavy. But you can't see the wires on that, so it's not a good example. So component 5, what is that?
Rectifier diode.
So
It's 20.
So number 5, does it have a label as a rectifier diode?
Oh, the rectifier.
Okay. So this right here. So for right now, we just want to call it a diode. But how is that different than number 8?
E is a lightning diode.
Okay, so 8 has a zigzag, so it's an LED versus just a regular D. So diode, light emitting diode. And then this one is a Zener. Is that how you say it? Zener diode? Okay. And then component 6. So this one's the one that's got a T and a pickaxe. What did you say? Okay, so it is a capacitor. 7, we just covered that. So resistor, I say it with confidence. And how is that different than number 9? Okay, so variable resistor, usually potentiometer.
Different levels of
Say that again?
you're able to control the power levels sent through the transistor.
So this specifically is changing the resistance. So crank it up, crank it down, changes the resistance. Really cool.
What was 10?
Oh, let me back up. Did I have a 10 on there?
Yes.
Oh, that's a Zener diode. You don't need to know that. I don't know if you need to know that for the general or not, but you definitely don't need to know that for the tech.
Well, I want to get it down anyway.
Okay, Zener diode is Zenier. And off the top of my head, I don't remember exactly what it does.
The voltage regulator.
Voltage regulator? Voltage regulator.
Thank you.
No problem. And then, of course, we've got all sorts of grounds here. All right, so another here. So component 2. We haven't covered this. Well, what do you think that is? It looks like a component that we've been playing, or what we've talked about.
I can't remember if this was, but I know, I think it's like that coil wire you like put on an antenna to like increase the bandwidth or whatever. Maybe?
So it's a capacitor,
Oh.
and so a capacitor with a line through it is a variable capacitor, and I cannot think of an example of one to save my life. Do you have an example of a variable capacitor,
Tune down on your radio.
like the VFO knob? VFO knob, so variable frequency oscillator knob, is part of a tuned circuit. Variable capacitors used for tuned circuits. Jacob.
The level, the wire feed speed on a wire feed welder, or the electrical control knob that allows you to adjust how much electricity you're putting into the welding when you're working with it.
Okay, I'm not that familiar with welders, but
Well,
maybe. I'm not sure if those are
wire feed
potentiometers.
welders have 2 knobs, one to control how fast the wire gets spit out with the electrical current running through it, and one to control how much electrical current is in the wire.
Okay,
I actually have one. I
okay.
took a class, and then he gave me $400 of welding stuff because of certain reasons.
Cool. I did some TIG welding a few summers ago. I haven't done any since. I should probably get back into that. So schematic 3. So this one, we've talked about the cold front. So what's the base part there in the schematic? It's a coil of wire. Okay, inductor. And so very similar to the resistor that we talked about, the potentiometer, was this arrow meeting doubling back on it. Okay, it's a variable inductor. And then, so we got grounds. Then we go to number 4. What's number 4? So antenna. So we haven't covered that, but that's the symbol for this goes out to our antenna so we can actually send the signal out somewhere. Any questions on this circuit? And I think this is on like page 22 or something like that.
21.
21.
Number 2 is a variable resistor or something like that.
Variable capacitor.
Variable.
All right. So we have some random components. There's only like one question in the entire 400 question test bank about these. So I just gave you what you need to know about these items. So a switch is an electrical component used to connect or disconnect electrical circuits. So the same with my Franken coffee maker, turn it on, we connect it, open it up, we disconnect it.
Fashioned coffee maker toggle switch,
Yes.
because that's what that is, a toggle switch.
And a fuse, which I just found out was that weird boxy symbol, is used to prevent an overload in the circuit. So your fuses are rated for certain amperage, and so like a 20 amp circuit or a fuse, a 5 amp fuse. And so if there's 6 amps that goes through that fuse, the little wire inside of it overheats and burns up. So it cuts off the circuit to prevent damage to your system. So there is one question in there that says, why should you not replace a 5 amp fuse with a 20 amp fuse? Well, because that would be stupid, but it would be because you would allow too much volt or current to go through that certain juncture, and it could damage whatever's downstream of that flow. So there's a lot of really fine pieces of equipment inside your radios. You can burn out your finals or just fry the entire thing if you increase the amperage of your fuse. A relay is an electrically controlled switch. I think there's actually a little magnet, so it's a tiny electromagnet, but they look like little black boxes. That's all you really need to know about relays. Meters displays an electrical quantity as a number. So if I get a multimeter, I click it on, the meter, that display, takes electrical quantities and displays them on your screen. So I can tell how many ohms are going through that circuit or how many volts are going through that circuit. An integrated circuit, you pop open any modern electronic device, and all it is the printed circuit board with all the components pre-assembled on there. Call that an integrated circuit. A regulator controls the voltage from a power supply. A shielded wire. So this could be an example of a shielded wire because I can't touch the electrical. I can't touch the positive or negative or ground, which is a good thing. So it prevents the electricity in here from coupling with my body and making me have a bad day.
Negative and ground.
Yeah, so we got positive, negative, and ground.
Shield refers to
Is it coax?
coax.
Oh, well then let me grab some coax.
Right?
So this is insulated wire.
It can't be shielded.
All right, so
It can
coax.
be, but and not unless there's a reason for it.
So here we have coax cable. So it's shielded. So it actually has 2 layers to it. It's got an internal, usually a solid core, and then it's got a dielectric, usually it's white. I don't know what it is on this one because I cut it open thankfully. And then it usually has a braided outer jacket.
White coating, and then the other wires are all covered in a plastic coating, and then all of that is covered in a even thicker plastic coating.
Pretty much. So this has 2 main layers to then transmit your signal, and this is a shielded wire, so it's not bothered by being out on the wet lawn as I'm transmitting, or else my transmission will get degraded by the wet lawn. Thank you, Tom. And rectifier, it changes AC into varying direct current. And so, as Mike pointed out in the page, whatever that was, this diode on number 5 is part of a rectifier circuit, so it's a rectifier diode. So this could be used to change the AC current, which I don't see an AC source, so I'm not quite sure about that. But what you do need to know about rectifier is it changes AC into varying direct current signals. So you use a rectifier here. My laptop runs off of, I don't know what the voltage is. Anyway, it runs off DC current. And this is right here, this box is a rectifier circuit that turns the AC current into DC voltage to run my laptop.
But doesn't the laptop then have to be converted into a AC current?
No, it does. All the components here use direct current. And so that's the same way if you have an electric stapler, this wall wart right here, they call these wall warts. It connects to a Raspberry Pi that runs on DC power. The charger for our radios usually has a wall wart that then converts, it's a rectifier circuit that then converts to DC power, then charge my radio. That's fine. Thanks, though. All right. Oops. All right, so that was actually all that I had for tonight. Does anybody have any questions or discussions? And Mr. Beam hasn't said anything else yet.
So next week is amateur radio signals. No,
So next week,
radio waves and antenna feedback.
yep, radio wave characteristics. So we'll definitely talk about the electromagnetic spectrum and antennas and feed lines. So we'll talk about those next week. Definitely.
Lines.
What did you say, Jacob?
I know something about feed lines.
Okay, so bring that to class next time.
I was just gonna.
Oh, you wanted to say it? Okay, that's fine.
Well, anyway, the line that connects to your amplifier and then to your radio, whatever, your handheld radio that you can put a little antenna on, or your police stations type radio, the ones with microphone type things. Those things, every time you make a connection between one thing and the cable, like if you have one cable and then another and you connect the two together in order to extend the longer one just a little more, it degrades the signal.
Yes, so we will
Why
talk.
It's just a better idea to have one gigantic huge one.
Okay, so we will talk about cables. We'll talk some about loss. So yeah, every adapter that you have does increase the amount of loss in that line. So yes, please read from let's go to the table of contents here. So please read about from page 24 to page 41 so covering these two chapters. And we're going to be meeting on Thursday, October 18th, 7:30 in this room. So if, I will send you an email so you can have access to the videos. It's just on my YouTube channel, and access to the slideshows, so they'll be on Google Drive. Any other questions or anything people want to discuss? Terry?
Is it too late to ask more people if they want to be in the class, or have you already got too far ahead?
Just let me know, because there's a lot of people that weren't here tonight that couldn't be here that are still interested. I've got, I can get more material to study. This PowerPoint, I recorded it. There were PowerPoints online. The video's on my YouTube channel, so we can make it work.
So all of these PowerPoint things you send us an email link?
Yeah.
Or-
So you'll have a link to this slideshow and then this video where we are talking.
It's okay if we are going to send this up to Jerry. too.
Right.
Okay. Let me end my stream here.
So you said